Welcome back. It's Dr. Pierce again, and I am so pleased and excited to be able to present content on the special senses and the related physiology to you in this portion of the neuroendocrine course. Similar to the sensory physiology section, I provided these videos, which are kind of broken down into more manageable pieces by learning objectives that let you navigate the content or preview the content in a way that makes sense for you in more manageable chunks, if you will. I have my learning objectives throughout this presentation as well. And as always, please don't hesitate to reach out to me, send me your questions, send me your feedback. I really appreciate it, and I look forward to navigating this content alongside you. These are the learning objectives for this content, similar to the learning objectives that I laid out in the sensory physiology and pain content from the last portion of the neuroendocrine course. These learning objectives are arranged in the same way, where you have what it is that you're going to need to do with this information, the clinical relevance associated with the objective, and then really what you need to do in order to fulfill the learning associated with this learning objective, which is in the underlined portion seen here. Learning objective 1 is about visual processing within cells and layers of the retina. So you know that old saying, the leg bone's connected to the ankle bone and the ankle bone's connected to the foot bone? Well, this is the 3 cells in the pathway that we are going to focus on for this learning objective, and that consists of the photoreceptor cells, either the rods or cones, and the photoreceptor cells are connected to the bipolar cells. The bipolar cells are then connected to the ganglion cells, and the ganglion cells are connected to the brain, indicating that those central processes coming off of the ganglion cells, they form the axons of the optic nerve, which eventually end up in the nuclei of the brain. So we're going to go over this set of cell signaling, what happens at the different junctions between the photoreceptor cells and the bipolar cells, and then the junction between the bipolar cell and the ganglion cell. You have learned a lot about the biochemistry of the rods and cones as taught to you by Dr. Kendi. So I'm not going to go into that information because that was very well covered in her lecture. We're going to pick up now with assuming a rod or a cone has been quote unquote activated by light or in other sorts of circumstances. What happens next? So this is a quick summary of rod and cone systems that I want you to keep in mind as we go forward. The rod system is heavily dependent on convergence, meaning many rods can connect to or synapse with many bipolar cells, but then that big number of bipolar cells can then converge onto one ganglion cell. And that's essentially how the rod system is able to operate in dim light, because that convergence kind of amplifies the signal from any one given rod. The cone system, on the other hand, has less convergence. It's essentially a 1-to-1-to-1 cell ratio. One cone connects with one bipolar cell, which connects with one ganglion cell. Anatomically, you've learned about the distribution of rods and cones across the back of the retina, with the density of the cones peaking right at the center of the fovea, and the density of rods peaking at about a 20-degree angle off of the center of that fovea. Of course, the blind spot is the spot where the optic nerve exits the retina. But I bring this up because I think it's really interesting to think about that 20 degrees off of center. Next time you are in a low light environment, let's say you're outside and you're looking at the stars, what I want you to do is try to really focus on one star and look and see how bright it is. And if it's twinkling and it's hard to see and it's really faded, you're staring really hard at it. That's kind of what it looks like. Now, what I want you to do is kind of take that focus and look just off to the side of the star, essentially what might be about 20 degrees. So just to the side of the star, and using your kind of peripheral vision, notice that the star suddenly seems brighter. When you stare straight at it, it's dimmer. But then when you look off just to the side, it's a lot brighter. And that's the functionality of those rods peaking at about 20 degrees off of center. And it's a really interesting phenomenon, and you'll notice it if you practice and give it a try. Again, now we're going to pick up again with where Dr. Kindy kind of ended her lecture, and that is to delve into the nuts and bolts of how these photoreceptors, the rods and cones, work. And it's at least in terms of the relationship between photons of light, depolarization, and then neurotransmitter release. The big takeaway here is that rods and cones work backward from the way that you would expect. Depolarization occurs, and let me pull up my laser pointer here. Depolarization occurs in conditions of darkness when no photons are around. Well, there's probably some photons around, but when the eye is not receiving bright light in conditions of darkness, that is when rods and cones depolarize. And the biochemistry of that process and why darkness depolarizes is what Dr. Kindy taught you. And that is kind of opposite from what you would imagine, because when you are receiving light, you're in conditions of brightness, the rods and cones hyperpolarize. Now, in general, we think of depolarizing cells are active, they're responding to something, and hyperpolarizing cells are kind of backing off, they're not responding to something. But that is why these photoreceptor cells work backward, because when you are in dark conditions, aka you're not receiving light, the cells depolarize. Okay, so let's talk about exactly what happens next after a rod or cone photoreceptor depolarizes, and that's down here in blue. Step one, they depolarize. Okay, now remember, depolarizing is in conditions of darkness, so you're outside and it's dark, or you're in a dark room, it's nighttime, anything like that. When a photoreceptor depolarizes, a graded potential is generated. When a graded potential is generated, the neurotransmitter is released from that photoreceptor cell. Now that makes sense. Whenever something depolarizes, we usually release neurotransmitters. So what is backward here? Well, the backward part is that neurotransmitter that is released acts like an inhibitory neurotransmitter. So whenever an inhibitory neurotransmitter is released, the thing it's talking to doesn't get activated. And that's essentially what's happening. We have a neurotransmitter released from the rod and cone. It acts like an inhibitory signal. And then the next cell type in the chain, remember the photoreceptor cell is connected to the bipolar cell. The bipolar cell does not depolarize because the thing that's talking to it, the neurotransmitter, acts inhibitory. And if this bipolar cell does not depolarize, then no impulse is sent onward to the brain. Therefore, you're not seeing anything because it's dark. So hopefully that makes sense. Okay, now let's look at the opposite set of conditions. Again, remember, photoreceptor cells, they work backward from the way you would expect. Now, let's look at what happens when you do receive light. You are standing in conditions of brightness. The lights are on, you're in a room, the lights are on, you're outside in the sun, anything like that. Your rods and cones, the photoreceptor cells, hyperpolarize. Now what? Okay, let's move down to the blue box. When a photoreceptor hyperpolarizes, the next step is a graded potential is not generated within the rod and cone. When it is not generated, no inhibitory neurotransmitters are released. So remember last time a neurotransmitter was released that's acting inhibitory? Well, now we're not releasing that. We're hanging on to those. Therefore, if you have a lack of inhibition, meaning you're not inhibiting anything, the next cell type, aka the bipolar cell, is allowed to essentially spontaneously depolarize. And that's what's occurring here. And then when the bipolar cell spontaneously depolarizes, a visual impulse is sent onward to the brain. And that is why conditions of brightness, aka when the rods and cones are receiving photons of light, you get a visual impulse sent to the brain, aka you are seeing something. All right, now we're going to get into more about this neurotransmitter that acts inhibitory. What does that really mean? Well, this all starts with the rods and cones and this idea that they are constantly releasing glutamate. Glutamate is the neurotransmitter of a rod and cone, and they're always releasing it. Now, the thing that changes isn't necessarily that the glutamate release starts and stops, because it's constantly releasing. It's the amount of glutamate release that is changing. If you think about the difference between a drip in your faucet and a waterfall, water is falling in both cases, but the amount of water is much greater in a waterfall than a dripping faucet. And that's essentially what's happening with the rods and cones. They're constantly releasing glutamate. It's either a flood of glutamate or it's a little bitty drip of glutamate, but either way, they're constantly releasing glutamate. All right, so let's get into specifics here. When you are in conditions of darkness, let me bring up my pen here. When you are in conditions of darkness, aka you're not receiving a lot of light, you're not receiving light, the rods and cones depolarize. That's what we said in the last couple of slides, because it works backwards from the way that you would think. And when rods and cones depolarize, they release their neurotransmitter, which is glutamate. But this glutamate is released like a waterfall. It is a flood of glutamate. That is why we say glutamate release is highest in the dark. And that's because it's like the difference between that dripping faucet of glutamate and a waterfall of glutamate. This is the waterfall of glutamate. And I have my cute little Batman symbol here because, you know, Batman lives in the dark. So Batman, he likes his glutamate, right? Okay, so glutamate release is highest in the dark. Remember, Batman likes his glutamate. So now let's talk about this. We have darkness, all right? Darkness is depolarizing a photoreceptor. A graded potential is generated. A neurotransmitter is released, and that neurotransmitter is glutamate. Now, you might be thinking to yourself, Dr. Pierce, I learned that glutamate is an excitatory amino acid. And you are completely throwing me off of my game because glutamate is excitatory. How can glutamate act inhibitory? Well, I said glutamate, in this case, the neurotransmitter, it acts inhibitory. Why? How is it possible that a glutamate, an excitatory amino acid, can act inhibitory? We're going to get into that in just a minute. But trust me, it does. Let's continue with our logic and make sure this makes sense. Darkness depolarizes photoreceptors. Glutamate release streams up to waterfall amounts. It's huge. When that happens, it acts inhibitory, and the next cell in the chain, the bipolar cell, does not depolarize. Then no impulse is sent to the brain, and you don't see anything. Okay, now that we've gone through what happens whenever we are in conditions of darkness, let's look at the opposite situation, conditions of brightness. Remember, rods and cones constantly release glutamate. It's either a waterfall or a slow drip, but they constantly release it. And then during the conditions of darkness, it's a waterfall. So that means the opposite in conditions of brightness. That's why I have my little sunshine logo here. In conditions of brightness, glutamate release is lowest. That is the drip of the faucet. It is still dripping, but it's a very slow, just a little bitty bit. And that is induced by the stimulation by photons, as you learned from Dr. Kennedy's lecture. Now, what happens to rods and cones in conditions of brightness? The cells are hyperpolarized. That hyperpolarization explains why glutamate release is lowest. Okay, now let's go through our series of logic and make sure this makes sense. In conditions of brightness, we have our little sun here, which is kind of a fun, it looks more like an amoeba than a sun, but That's my little sunshine. May add one more there. There you go. Conditions of brightness, we have a photoreceptor that hyperpolarizes. A graded potential is not generated. That inhibitory neurotransmitter, in this case, it's still glutamate. And I know what you're thinking. You're thinking, Dr. Pierce, glutamate's an excitatory amino acid. I know, it is. It really is. And we'll get to that next. But in this case, we have hyperpolarization. No glutamate is released. And when that happens, the bipolar cell, that's the next cell in the chain, remember photoreceptors are connected to the bipolar cell, they spontaneously depolarize. Essentially, they're allowed to depolarize because there's no more inhibitory neurotransmitter putting the brakes on them. And when this happens, a visual impulse is sent to the brain, and we essentially see stuff. So make sure before we keep going forward that this kind of series of steps makes sense to you. Be sure to connect photons with either hyperpolarization of rods and cones and why that occurs, and then the decrease in the amount of glutamate that's being released, and then connect that with the fact that a visual impulse is sent to the brain because the bipolar cells are suddenly allowed to spontaneously depolarize. Okay, with that, next we're going to look at why is this glutamate magically acting inhibitory. Okay, so obviously I think that this is kind of funny because I remember learning and memorizing all those excitatory and all the neurotransmitters, and I had it just down in my brain that glutamate is excitatory. And indeed it is. And glutamate is excitatory specifically when it is working with its normal receptors. And as you learned, the things that bind glutamate are either NMDA receptors or non-NMDA receptors. AMPA and kyanate are together, we refer to those as the non-NMDA. NMDA. So glutamate will bind to an NMDA receptor or a non-NMDA receptor. Now, bipolar cells are special. They express a special receptor that can bind glutamate, and that is called mGluR6, and that stands for metabotropic glutamate receptor subtype 6. Okay, what that means is mGluR6 is a G protein coupled receptor. It's a GPCR, and it closes cyclic GMP gated sodium channels. Okay, if you don't remember what that was, be sure to take a minute and go and look up what GPCRs and cyclic GMP gated sodium channels are. I'm not going to make you learn that biochemistry for our purposes, but I just want to make sure that that makes sense to you. So these cyclic GMP gated sodium channels closes when glutamate binds this receptor. And what happens when a cation channel closes? Okay, what happens is you get that hyperpolarization effect. And that is similar to how light transduction and photoreceptors work. Okay, so this allows a typically excitatory neurotransmitter like glutamate to act inhibitory. Not because glutamate is inhibitory, it's because the receptor it's binding to is inhibitory. Therefore, when glutamate is released in the waterfall from the rods and cones cells, that results in sodium channels closing in the bipolar cell. Okay, and when sodium channels close, the bipolar cell does not depolarize. All right, now, essentially the same story goes on for the ganglion cells. Remember our pathway. Photoreceptors connect to the bipolar cell connects to the ganglion cell. Now, when a bipolar cell is activated or depolarizes, it also releases glutamate. Glutamate is still our neurotransmitter of the day in this pathway. However, the glutamate receptor that's expressed by ganglion cells is the normal NMDA or non-NMDA receptor that you would expect it to be. Therefore, when you have depolarization of a bipolar cell, you will subsequently get excitation of a ganglion cell. And if it is to enough of a degree, you can generate an action potential in that ganglion cell because they will then become the axons of the optic nerve, and then therefore you have vision initiated. Now, what happens with the central terminal of those ganglion cell axons? Well, it will eventually go on to either one of the relay nuclei or the direct targets of the retina, and eventually to the visual cortex. In the visual cortex, we can release glutamate again. So glutamate is still the neurotransmitter of the day. Now, this is the same picture from earlier on. This is summarizing what we've gone over so far, and we have our photoreceptor cells, our bipolar cells, and our ganglion cells. The gray box is summarizing conditions of darkness. The yellow box is summarizing conditions of brightness. You see here that during conditions of darkness, the photoreceptor is depolarized. Next, calcium channel is open, neurotransmitter is released. But that neurotransmitter that's coming from the photoreceptor cell is glutamate, and it is going to bind mGluR6, that special inhibitory receptor. When you have an inhibitory receptor activated, you get a inhibitory postsynaptic potential, aka inhibition here. I-T-I-O-N. My apologies. I know that doesn't probably spell out very good. But IPSP stands for inhibitory postsynaptic potential in the bipolar cell. When you have an IPSP in a bipolar cell, then it's not activated. Then no neurotransmitter is released from the bipolar cell, and you don't have any activation of the ganglion cells and NMDA receptors. When you have no activation of an excitatory receptor, you get no EPSP. EPSP stands for excitatory postsynaptic potential. No action potentials are generated, and you have no vision. You have nothing to see. Contrast that with conditions of brightness. Okay, you have a photon of light. You have a hyperpolarized photoreceptor. Again, be sure you have that content down from Dr. Kendi about why photons hyperpolarize photoreceptors. During hyperpolarization, calcium channels are closed. No neurotransmitter is released. When you have no neurotransmitter released, in this case it's the glutamate going to bind to the mGluR6, it's not happening at this junction between the photoreceptor and bipolar cell. That means that you have no IPSPs, meaning no inhibitory postsynaptic potential in the bipolar cell. And when that happens, you get a spontaneous activation or a spontaneous depolarization of this bipolar cell now. That is why down here at this last junction in this cell type, we have release of neurotransmitter. This is, again, it's still glutamate, but it binds to the NMDA receptor on the ganglion cell. When you have binding of a positive excitatory neurotransmitter receptor, you get an excitatory postsynaptic potential in the ganglion cell that will generate action potentials if it's to a big enough of a degree. And when you get action potentials, you're going to have a signal transmitted to the brain that indicates that you have seen something, you have vision now. Somewhere in the brain, whatever the direct target of the retina is, this central terminal is going to release glutamate again into the next cell in the pathway. And that next cell in the pathway will use NMDA to recognize that glutamate. Now this is the last slide in this section of the video. This is a summary of the learning objective. So be sure to compare what the learning objective says to the information in this table. Read over it, make sure it makes sense to you. I would also challenge you to blank it out and see if you can summarize this information on your own without looking it up. Thank you again. Be sure to contact me if you have any questions, and we will pick up with the next video in looking at the direct targets of the retina in the brain.